Yeah, good morning everyone. Welcome to the second day to the IPv6 Security Summit. I hope you enjoyed the dinner, at least the ones who joined us yesterday. Yeah, welcome with me please Fernando Gont, who is now talking about recent IPv6 security standardization efforts. And now, your turn.
Yeah, thank you. Good morning. My apologies for my voice. I don't know if it has to do with walking around with not a lot of clothing or what, but I can barely talk. This presentation is about recent IPv6 security standardization efforts. If last year you attended the V6 Security Summit and you attended my talk, I gave a similar talk. So the idea for the presentation that I'm going to do today is essentially cover new documents that were published in the meantime, that were not published at the time when I did the previous presentation. And also there are cases in which fortunately, we made some progress with those documents at the time, so we have, let's say, some news in that area. When it comes to the motivation of this presentation, I mentioned this already in other talks. If you think about IPv4, the IPv4 world, essentially everything that has to do with mitigations were added once we were hit by different kinds of vulnerabilities. If you think about, for example, SIM flooding attacks, predictable TCP sequence numbers, predictable TCP ephemeral ports, and so on, usually all those things were implemented in a bad way from the beginning. And then eventually, when we were hit by different kinds of attacks, there were documents that were published on the topic with mitigations, or at least many implementations were updated to mitigate those issues. A problem with that is that obviously we don't want to repeat the story of IPv4 or the IPv4 world in which the mitigations were added once we were hit by the problems already. So you have probably seen this movie. And the idea of much of the work that I've done is to essentially try to have an alternative path to that. So rather than going on the way of being hit by many different issues, to try to incorporate mitigations in the specs and in implementations too, so that those issues can be avoided. As I said before, I'm going to cover documents that have been published from the time I did the presentation last year, or documents that have seen some sort of process of progress. And at the same time, I'm also going to mention documents that should have made progress, but for a variety of reasons were stuck. First of all, I will start covering the topic of IPv6 addressing. Of course, the syntax and the semantics of IPv6 addresses are known by everyone. Essentially, you have the global routing prefix, some bits for subnetting, and an interface ID. And the idea is that since in IPv6 you have many bits for the interface ID, there are many more creative things that you can do, as opposed to the IPv4 world, where you only have a few bits for the host ID and there's not much that you can do. There are different ways in which you can set the interface ID. As you know, let's say the standard way to set the interface ID when you do Slack or stateless address auto configuration is the first one, this one, in which you embed the MAC address. But there are other ways in which you can possibly set the interface ID. So some of these are described here. For example, you can embed your IPv4 address in the interface ID in this way. You can actually even write the address in that way. So all the relevant APIs, they support this format. You can also set the interface ID to small values. This is what we typically refer as low byte addresses, and so on and so on. If you think about the security and privacy implications of IPv6 addresses, and let's just assume for the time being that we are talking about addresses that embed the MAC address, okay? Because there are many different ways in which you can set the interface ID. One of the implications is that you can correlate network activity over time. And that's kind of like simple. You have a field that is 64 bits long, which is like a globally unique number, because MAC addresses, at least in theory, are supposed to be globally unique. So if you see, for example, some sort of interface array, you see some IPv6 address at some point later in time, you see the same IPv6 address, you can easily tell that that's the same node. Why? Well, because if we are saying that we embed the MAC address and the MAC address is globally unique, then the interface ID is leaking out the identity of a node. Things can also be like actually worse, because that of correlating network activity in the same network is not that bad. But things get worse when you can correlate the network activity of a node as it moves from one network to another. The idea is pretty simple. If we are saying that the interface ID embeds the MAC address and that MAC address is globally unique, that's kind of like embedding a serial number, a unique serial number in the interface ID. So for example, we could have a node that connects to one network and it gets this IPv6 address. Of course, in bold, here you can see what's supposed to be the interface ID. And then let's just say that the same node moves at some point in time to this other network. Of course, the prefix will change because the network is supposed to be a different one, but the interface ID is the same. Why? Because we are always embedding, again, the MAC address. So by looking at the interface ID, you can essentially identify the node, and that's something that you don't really want. Of course, if, for example, you embed in the interface ID a MAC address, MAC addresses do follow patterns. So, for example, the upper 3 bytes correspond to what is referred to as the OUI, or Organizational Unique Identifier, or something like that, which is a value that identifies the vendor that manufactured the network interface card. And you could, to some extent, assume that the low-order 3 bytes are, to some extent, random. But the point is that if there is some structure in this field, in the interface ID, then an attacker that wants to scan for alive nodes doesn't need to scan the whole /64 space, but can actually target specific patterns. And the final one, which is from my perspective not as important as the previous ones, is that the MAC address also leaks information about what's the vendor that produced the device. So if for some reason you knew that there is some, let's say, some bug or some vulnerability that affects, let's say, devices manufactured by Realtek, just by looking at the IPv6 address, you could tell that the device is manufactured by Realtek without any need of even doing like OS, operating system stack fingerprinting or that kind of stuff. Let's look a little bit more into detail about these topics. The first one is about scanning. I have kept this slide for a while, and unfortunately, to some extent, there is still some truth to it. So you still find people that claim that V6 networks are not possible to scan. It's funny because a few times I've been at conferences when the previous speaker made exactly the opposite argument, and then I had this slide in my talk. So you see these sort of claims quite a lot. This is one of the myths typically associated with IPv6 security or with IPv6, that if you want to scan a V6 network, it would essentially take like ages. So usually when you see these sort of claims, you have like two options. One of them is assuming that the guy that said this sort of thing was on drugs, and the other one assuming that he had some sort of reasoning to get to that conclusion. So I assumed the later, and I thought or I assumed that people making these sort of claims, they thought or expected that if an attacker wanted to scan an IPv6 network, they had to go through the entire /64 address space, which of course in that case, yes, it would take like ages. But if you want like a more elaborate answer, there's this draft that we authored that has been stuck in like waiting for it to be sent for publication. Is draft -ITF OPSEC IPv6 host scanning, which describes not only address scanning, which is the topic that we are discussing right now, but it also discusses like many different techniques for network reconnaissance. At some point in time, what we tried to do was to find out whether the addresses were really random. You have probably, or you may have seen these results. So what we did, we measured public internet servers and tried to find out or try to analyze if their addresses were following any patterns. So this is what we found, for example, for web servers. It doesn't really matter, or it doesn't make much sense to go into the specific details, but what's important in here is that if you look at the distribution of addresses, the addresses clearly follow specific patterns. So it's not that they are random. For example, these addresses in here are what we call low byte addresses, which means that the address of the server in that case was the prefix and some small value. So that means that you set the interface ID to all zeros, and just the last byte or so was set to a small value. This is the same stat for mail servers, same stat for DNS servers, which, well, you can easily tell that the patterns are even more clear. So, for example, if you were an attacker and you were trying to find, a live systems, you wouldn't just try random addresses or even addresses that embed MAC addresses. You, of course, would try to target these addresses because, like, almost 75% of the addresses are there, okay? Then you could think about, well, how do you find these other ones? Yeah, I mean, these ones could be interesting or important, but of course, when an attacker is trying to find systems to attack, he is going to try, first of all, to find these addresses that are, easier to find. Should I move myself to I think that it's coupling the microphone with the speaker. Is that correct? Yes. Yes. Okay. Or maybe this was that one. So when it comes to mitigation of these issues, the only stuff that had been, let's say, published by the IETF, it was what you probably know as IPv6 temporary addresses that are randomized and they change over time. But the problem with those addresses is that they are generally painful from an operational point of view. So you have a network, and let's say that you find that yesterday there was some system that was trying to infect some other systems on your local network. Well, if then you go to that network and try to find out what was the device, and you just don't know because the address changes all the time. So that's something like could be let's say useful from a privacy point of view, but when it comes to the people operating a network, usually it results it's actually painful. And this is a reason for which many enterprises, when they deploy V6, they just disable temporary addresses altogether. So what we tried at the time, and this is something that is like a change or like some sort of progress from last year, we finally got this RFC published. This is what used to be draft IETF 6-man stable privacy addresses. So this RFC got published already. This RFC essentially proposed like an alternative way to generate IPv6 addresses. And the idea is extremely simple. You generate the interface ID by hashing, this is a hash function, the prefix, and for the time being, you can forget about every of the other parameters, just think about the prefix and the secret key, okay? So you compute a hash over the prefix and a secret key. The secret key, of course, is secret. So if you connect to this network, the prefix is going to be some sort of prefix. So you get some result for the hash function. Let's now say that you move to a different network. Since the prefix is going to change, you get a different interface ID. But if you move back to the original network, you get exactly the same interface ID. Why? Because the prefix didn't change. So the idea of this scheme is that while you stay in the same network, your address is always the same and stable, but as you move from one network to another, your interface ID changes. So that's something that is that we did on purpose. So we want, from the point of view of the local network, the address to be stable but not predictable. So you always get the same address, but it's a random number. So from the point of view of the guys running the local network, your address is always the same. So if they find that your system was trying to attack other devices, infecting other devices, and so on, well, the mapping from v6 address to node is going to be straightforward, because every device always gets the same address. But as you move from one network to another, the interface ID changes, which means that it's not possible to correlate network activity across the networks. And at the same time, since the interface ID is going to be a random value, that means that if an attacker wanted to scan that network, well, in that case, he should try, or he would need to try the whole /64 address space, which would mean that, at least in theory, such scanning attacks would be impossible. As a kind of, I described this already, as a kind of update, this is something that I don't know if it's public, but that I can share. There is they are working right now to commit this to Linux, at least to, well, I don't know that much about the internals of Linux, but apparently they are implementing this in Network Manager, which is what at least you use when you have the the graphical interface for generating the addresses. And the folks from Google are very interested in committing this to Android, so that's a good thing. So this is in the works, but I guess that we could expect that this year we will finally be able to find this in the in those operating systems.
But so I can assign multiple IPv6 addresses to an interface. So if I want to do some evil stuff,
Yes.
organize myself a second IPv6 address.
Yeah.
The evil stuff then, so they will still not find me.
Yeah. Well, so the thing with in all these cases, what we are assuming that nodes, first of all, they take the address that they are not, let's say, maliciously generating their IPv6 addresses. So this could be used for example, for the case in which you have a host, and there's no such a thing such as let's say a virus trying to configure a different address. Of course, in that case, yes, you're dead to some extent. Okay. So what we're trying to address here is a case in which, in all legitimate scenarios, there's no one explicitly changing the addresses, and you want to be able to, to some extent, be able to correlate network activity. Of course, nothing prevents you from even manually configuring a different address. Okay. Another thing is that, for example, when you use this scheme, you are mitigating, things such as, network activity correlation. Of course, in the same way, you could manually nowadays change your address so that your activities cannot be correlated, but, most people probably wouldn't do that, okay? So as I said before, there's a Linux implementation in the works. I don't recall exactly if by the time I did this talk last year, these guys were working already, but there was some folk that was, I think at the time, he was freelancing, so to speak. The guy is now working for Red Hat, and they are, let's say, putting more effort in getting this committed, to Linux, which is a good thing. But that in v6 you have essentially two different mechanisms for automatic network configuration. So one is Slack. The other one is DHCP version 6. When it comes to DHCP, there is the DHCP version 6. There's, let's say, no formal recommendation on how a DHCP version 6 server will select the addresses that it tries to lease to the clients, right? So there have been cases of DHCP version 6 servers which just generate incremental addresses. And of course, there are other cases in which they just randomize the addresses that they lease. So what we try to do here is to port exactly the same scheme that we did for Slack for the DHCP version 6. Of course, the main difference between the two schemes is that in the case of Slack, the system that is auto-assigning the address is the one generating the address, whereas in this case, in the case of the DHCP version 6, is the server that needs to generate the address to be leased. So in a very similar way as in the case of Slack, the interface ID is computed as a result of hashing a number of parameters. As you can tell easily here, there's the prefix and the secret key. These are the same two parameters that we were employing in the similar scheme for, for Slack. The stuff that has changed here is that, for example, rather than having an interface identifier, which we had in the previous, expression, here we have this value, ID, which is, a parameter that you have in DHCP version 6, which somehow identifies the network interface. So it's kind of like the same thing, but in DHCP version 6 speak. And then we have this client DUID, which is essentially like a client serial number. So the idea is that we use the prefix, we use the secret key, but we also want to use a value that will change from one client to another. If not, all clients would get the same addresses. And in the same way, we want to use some value that identifies the network interface card. So think about, for example, some host that has two network interface cards. The client ID would be the same if it's connecting to the same network with both interfaces. Prefix is going to be the same, secret key is going to be the same. So it's going to be this value, the one that will result in different addresses for each of the interfaces. So that's essentially the idea. One thing that it's interesting from this scheme, that let's just assume that you have, for example, for resiliency purposes, you have two different DHCP version 6 servers on the same network, okay? Now, if your DHCP version 6 servers were to assign just, randomized addresses, then depending on the DHCP server that leases the address, you'd get a different address, okay? So again, let's say we have two different DHCP servers. If the one that is leasing me the address is this one, it might probably produce a stable address, but some sort of address. Now, if now it's this other server, leasing the address, the result will be different. What you can use, and there are proprietary protocols to do that, they can synchronize the address list database, okay? So you have some protocol that allows both DHCP version 6 servers to communicate with each other, so that they say, okay, I have been granting this address, so if you have to grant the same address to the same node, use this specific address. But again, the mechanisms or the protocols that have so far been specified for that are proprietary. And the other thing is that, again, you need additional machinery, right? A protocol to synchronize the two servers. Now, if you think about what would happen with this scheme that we are describing here, if you have two different DHCP servers and you configure exactly the same secret key on both servers, they will produce exactly the same addresses. Not because they are synchronizing the databases, but actually because of the algorithm itself. I mean, if all the parameters are the same, of course the result is going to be the same. So the prefix is going to be the same because it's the same network. These values essentially have to do with the client, so they are going to be the same. Same thing here. And secret key depends on what you configure. So again, you configure same secret key on, let's say, multiple servers. They could be 5, 10, whatever number of servers you want. And all of the servers would end up producing the same addresses. So this is something that it's like a nice side effect of implementing this scheme. This document was adopted by the DHCP working group in November last year. And my plan is to have this shipped for publication during the next month or so. Whether that goes an easy way or not, it's a whole different game. But I think that from my perspective, the document is pretty much done. And the nice thing is that folks from, for example, ISC, which is one of the companies that produces DHCP version 6 software, support this stuff. Or at least they supported that on the mailing list. If you ask me whether that means that they are going to implement it, I just don't know. We talked about this already. Other documents that are related to this stuff that we have just described. So as a kind of side comment, when I was describing before RFC 7217, okay? The mechanism or the algorithm for producing addresses for Slack. When I published that document, kind of by the end of 2011, the same document essentially did three things at the time. One of them was to specify the algorithm, okay? The other thing was that the document was describing the security and privacy implications of the traditional Slack addresses. And the third one was that the document was saying, well, if you were, generating your Slack addresses by embedding the MAC address, you should do this scheme that we are proposing here, okay? Specify the algorithm, formally replace the traditional Slack scheme, and also describe the security and privacy implications. For reasons which, let's say, I don't necessarily know or share, the relevant working group at the IETF decided to split that document into 3 different pieces. One is RFC 7217, which is the one that was published. The other one is this one, Address Generation Privacy, which essentially describes the security and privacy implications. So it just focuses on that, and it doesn't only focus on the, on the traditional Slack scheme that embeds the MAC address, but describes the security and privacy implications of essentially every known interface ID generation mechanism. This document is like pretty much done, so we are waiting for the working group chairs to send it for publication. I would expect that it should be published as an RFC this year. And the other document that we published on this topic is this one, Default IIDs. What this document does is extremely simple. It says, if you are doing traditional Slack addresses, you should not do that anymore. You should do RFC 7217. If you ask me, did we really need a separate RFC? I don't think so, but this is what we did. If you want to find a reason for that, is that at the time that RFC, or what was the internet draft version of RFC 7217 was adopted, like the working group wasn't sure whether it was the right thing to replace the traditional Slack scheme. So from my perspective, it was like, well, while you decide or while you make up your mind whether we have to replace the traditional, Slack scheme or not, okay, we can, let's say, focus on standardizing this scheme. So now we have 7217, which is like an alternative way of generating interface ID. But no one tells you whether you should do traditional Slack or 7217. So this document essentially says that. I was expecting this document to be extremely straightforward and to be like published as an RFC extremely quickly. Life always surprises you with alternative paths. So there was like discussion on this topic. For example, there is, as a kind of brief summary, you have this, how should I refer to it, like what is called 6LoWPAN, which is using IPv6 for low power personal area networks. So these are like very, let's say, constrained devices, and for a number of reasons, they sort of need to use the traditional Slack addresses. For me, that's something that they shouldn't be using. They shouldn't be doing that, but they do. So they were essentially requesting us to relax their requirements a bit for them. I wouldn't do that, but the 2 possible options was to continue fighting that one for a long time, or to say, okay, well, do whatever, but for the general case, you should do this. So this is essentially what we did with this document. So we say, if you are doing 6LoWPAN, okay, well, you can do whatever you want to some extent, but for the general case, you should do 7217. Yes, you were going to ask a question?
I was asking on which track this draft will be going. Will it be a
standard track, yeah. Okay. Yes. When it comes to 7217, which for me, I was just about to have like a mental collapse. So after going, through all the process of, fighting for the document to be adopted and, being sent for final publication, while it was being reviewed by the ISG, which is the group of area directors, there were guys that had the idea to publish 7217 as an informational document, which means that we could have never made that, implement that because it was an informational document. So I don't even know the reason, but I get the planets were aligned, and we ended up publishing the document as a standard track. But we were like this close to have the document published as informational. So it's crazy. At times, you say that you went through almost the entire process, and everything is done, but there's always room for surprises. But this is when it comes to this document, I kind of thought about this document as a kind of personal battle. a personal successful battle, because I have other battles that were not successful at all. But the fact that we were able, at the time when I presented this document for the first time, like in 2011, even people that nowadays support this document were against this document. And I don't know if I ever mentioned this story, but there were, for example, guys working for vendors of mobile phones that essentially were strictly against this, and they were arguing things such as, well, why should you have privacy in your mobile phone? Of course, they didn't say that on the microphone, but they did say that. Actually, you have... Yeah, but I'm saying, that's true, but I mean, making that sort of argument for me was like, I couldn't believe what I was, hearing. But yes, things happen. So these are, again, the documents that we have on this topic, address generation, privacy, and default IIDs. Both of these should be published this year, I would expect. So some stuff on V6 extension headers. There's quite a lot of stuff that I'm not going to mention here. For example, there's RFC 7112, the one that forbids the use of long IPv6 extension header chains. That one was done and published like more than a year ago, so it's old to some extent. So I'm going to describe other stuff. As a kind of very brief introduction, because this stuff is probably known by most of you. So this is a structure of a V6 packet. And if you wanted, you could get to a packet structure such as this one, where you have the fixed header, a couple of destination options header, and the upper layer protocol, such as a TCP segment. Okay? So in theory, this structure of V6 packets leads to increased flexibility and blah, 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 blah. In practice, we know that this is not that much the case. This is the format of packets that employ fragmentation. As you already know, fragmentation in V6 is implemented by extension headers, as opposed to just some mandatory fields, as in the case of IPv4. Let's now talk a little bit about, so that was the theory when it comes to extension headers. So let's talk about the reality of extension headers. So first of all, for many, many different reasons, you might need to find the upper layer protocol in a packet. This tends to be like extremely painful. This is a case, the one that I was describing before, that thankfully or fortunately is not valid anymore. Is the case in which you have this original packet and you fragment it into these two pieces. And as you can see in this case, you have the extension header chain fragmented, the extension header chain itself fragmented into different pieces. So the first fragment does not even contain all of the extension headers, okay? RFC 7112, if I recall correctly, was the one to forbid this. So, I mean, you shouldn't see these packets anymore. If you were seeing them, or if you see these packets, you are free to drop them. But even then, even if you don't see these kind of packets, like fragmented traffic, even these packets are like painful. If you have, let's say, a firewall device, that means that in order to be able to look at the port numbers, you have to jump through all of the extension headers. I don't know if you follow some of the IETF mailing list. Right now, there's some sort of interesting discussion in the V6 Ops mailing list. There's an internet draft that I co-authored that is being discussed. And one of the interesting comments that I read this week, it was from a guy that I know, Brian Carpenter, and he was essentially saying that he had been speaking with people working on hardware, hardware implementation of things or protocols, and this structure is essentially painful, and it's known to be painful to implement in hardware to any guy doing hardware implementation of stuff. Unfortunately, this is the design that we have, so there's not much to do. There's people that argue that we should probably deprecate extension headers altogether. I don't have much of a strong opinion on that, but the stuff on which I do have a strong opinion is that of deprecating extension headers would have like a very, 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 very hard time at the IETF. So no matter whether that makes sense or not, it's an idea that in practice it wouldn't fly at the IETF. So A brief discussion about the security implications of extension headers. So if, for example, you process the extension header in software, the use of extension headers can lead to denial of service situations because it may be CPU intensive. While we were having dinner yesterday, one of the guys mentioned that he had this router that was employing all the time at least 10% of CPU, and that was because when he was trying to enforce IPv6 ACLs, that of enable any IPv6 ACL by itself caused IPv6 packets to be processed in software. Okay, so again, if the guy didn't have any ACL at all, the packets could be processed in hardware. But that of just enable any sort of ACLs on v6 packets caused all the packets to be processed in software. What was the end result? As you might expect, he disabled the ACLs, okay, for his particular scenario. So this is one of the problems that extension headers are known to cause. That processing the extension header chain is expensive. Another thing that is usually associated with extension headers in this particular case with the fragment header is that fragmentation is insecure. On one hand, one of the reasons for which people deem fragmentation as insecure, so to speak, is because fragmentation is, or reassembly in particular, is a stateful process. So if you are a node and you receive a fragment, you need to keep that fragment in memory to be able to reassemble that fragment with other fragments. And of course, at the point in which you require a node to keep something in memory, that means that the attacker can send lots of fragments, and all out of the sudden you need to decide what you do with all of the fragments that you have in memory. So that's one of the reasons. That reason, or that topic can be exploited for denial of service purposes. The other one, which is known for more than, let's say, 15 years from the IPv4 world, fragmentation, can give a network intrusion detection system a hard time, because you fragment the packets in tricky ways, and then that means that a system trying to monitor or understand the fragments, can essentially fail. The other one is that, unfortunately, even when v6 fragmentation is extremely similar to big 4 fragmentation, we had lots of bugs in the IPv4 fragmentation and reassembly code, and we also have lots of bugs in IPv6 fragmentation and reassembly code. So the thing is that even let's say routers have been found to have bugs in this area, so many people started to associate fragmentation with problems. That is not necessarily the case. I mean, it's not that vendors should produce buggy code, right? But in practice, it happens. So that's the reason for which you will find that many networks they just disable or drop packets that employ any extension headers, not just destination options or the like, but even fragmentation. What else? So as a result of these considerations, what happens is that many operators actually filter packets with extension headers. To some extent, this is not very problematic because for the most part, we don't really rely on extension headers for anything. So there's not really a protocol that, for example, relies on the use of IPv6 destination options. So in practice, you are blocking some sort of packets that in practice you don't need. The only packets that are, or that could be problematic is IPv6 fragments. Those are packets that we can, that at least at some point we might need to rely on them. For example, DNS traffic might result in fragmented traffic, but still when it comes to fragmented traffic, many networks actually filter those packets. So, the end result of this is that if you employ v6 extension headers, that is likely to result in packet drops. Since the last 2 or 3 years, we try to produce measurements regarding the extent to which packets with extension headers are dropped. So this is the drop rate for packets that employ destination option header of 8 bytes, hop-by-hop options of 8 bytes, and this is just fragments of 512 bytes. I mean, this is something that you could expect, dropping hop-by-hop options, because these packets, generate CPU or trigger CPU use in the intermediate routers. But this is something that you probably wouldn't expect, and even less this one. So this means that, for example, even name servers, they filter fragments. And name servers themselves might be needing fragments, okay? So to be honest, I think the first time that I did some sort of very rough measurements, which that probably was 2012, I think, I was kind of like surprised by the results. And then we presented this there, and so when you have an IETF meeting on Sunday, like formally speaking, before the IETF meeting, there's a group that's called the IEPG. I don't even recall what that stands for, but let's just say that it's a group of people that is more of practitioners, so to speak, people with a more practical background as opposed to just theory. And we presented the results there. We saw a lot of interest from the community from the community. So me and a number of other people, we ended up doing more and more measurements on the topic. This other slide shows so in the previous slide, what we say is, well, if you send packets with extension headers, for example, in this case, you get a 40% of packet drops, okay? Now, the question is, well, in those cases in which your packets are being dropped, so we are assuming already that your packets are being dropped. So when your packets are being dropped, are they dropped by the final destination, like the destination IS, or are they dropped by some intermediate system? So this is what we measured. This is the drop rate by different autonomous systems. So not the destination autonomous system, but a transit autonomous system, okay? So that means when packets are dropped, so given that packets are dropped, what's the rate in which, packets are dropped by a different IS? So you get about, from almost 10 to 50%. And this is kind of like really ugly. Why? Because it's not just the destination of your packets that is saying, I don't like your packets, but it's actually the network itself. So it's actually worse. So you don't even, at times, you don't even get to the destination, but in the middle, the network is dropping your packets. So the first couple of slides, this one and this one, we produced these results by measuring the list of websites that are published in the World IPv6 launch day, which are not that many size, maybe something like 1,000. And then we did the same sort of measurements, but with the Alexa's top 1 million websites, okay? Well, websites and also mail servers and name servers. If you were yesterday at my talk on the V6 Toolkit, I briefly described, how we ended up grabbing addresses for web servers, name servers, and mail servers. So you can see that, while the drop rates may vary like a little bit, kind of like the percentages are the same. So destination options are dropped, but not that much. Then hop-by-hop options are extremely largely dropped, and fragments are also largely dropped too. When it comes to drops by different autonomous systems, well, these are the stats that we got. So you can see that I didn't really come up with an explanation regarding why this looks like very different from this to some extent. So these two are kind of like similar, but this one is different. Yes?
When you analyze the Alexa top something,
Yes.
then you will probably get some ASs from big data centers or whatever here more often than others. So probably your results are skewed, or you have some ASs
Yes, that's true.
serving maybe 50% of your.
Yes, you're right.
thing.
Yes, that's a good explanation, yes. So what we did for the measurements, we discarded duplicate addresses, but you're right that you could have different addresses but belonging to the same AS. So yes, that's very likely. There are other things like, variations of this that, we could have implemented to try to, get different views, such as, for example, not just filtering duplicate addresses, but filter or consider that two addresses that belong to the same /64 are actually duplicates. Because if something that goes to, let's say, FC00:1, blah, 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 1 is filtered, well, a packet that goes to the same address but blah, 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 2 is going to be filtered too. So those are variations that, yeah, we could probably, implement.
I would assume mainly CDN.
Yes, yes, yes. So there were like, I think that in one of the first time that I presented results on the topic, I produced measurements discarding duplicate addresses and even not discarding duplicate addresses. If you don't discard duplicate addresses, you get like some kind of like intentionally weighted results. So let's say like the IPv6 addresses that are hosting more sites get like more weight in the results. So I would say that both alternatives are interesting. They give you like different perspectives on the topic. But bottom line, at the end of the day, I think that what's interesting from these results is that packets with extension headers are dropped, and to a large extent. Yes.
There was yesterday also a presentation from Eric Winken.
Uh-huh.
He also did measurements on this, and he said that he never really experienced that any of his packets with extension headers are dropped. He also said, I'm not sure which extension headers he used. I'm sure that he didn't use the hop by hop.
Uh-huh.
But so he has also like this own script on his website.
Uh-huh.
You visit it and it sends you a ping with extension header to check if it's working. He said, for example, from here, this network commands, it's no problem. So you can send extension header.
Uh-huh.
So maybe it's interesting for you.
Well, I received a comment from Eric. What I can say, so I asked whether his measurement results were public, and he said that they were not. So I wasn't able to analyze that. So that's one thing. The other thing that, even if, he also mentioned that the measurements that he did were like rather limited. That doesn't mean that if he did more measurements, the results would change, but they might be limited or biased to some extent. And the other thing is that, let's say we are measuring different things. So what he's measuring is whether extension headers work from a server where he knows that are not filtered to a client. Whereas what we are measuring here is whether extension headers work from a client to servers, okay? So what I can say from these results is that if you try to communicate with public servers, packets are largely dropped. And we have a document. I'm going to mention the file name like later, but in our interface, in our internet draft, we describe like step by step how you can reproduce these results. So it's not something that I can, I cannot tell you why, but I found blah blah. So this is something that you can reproduce, and you can measure that yourself and drive your own conclusions. Let's just say that I was saying that there's right now there's some discussion going on the V6 Ops working group mailing list regarding this, and many people see or have seen this sort of measurements as, let's say, rather controversial. There's the people that are like more, let's say, conservative, and they don't like to hear that something that is supposed to be a core part of IPv6 doesn't really work as expected. And some folk have also mentioned that, for example, Cisco is pushing segment routing, and segment routing employs extension headers, so it probably doesn't make much of a good marketing for them to be employing extension headers, and then us coming up and saying, extension headers don't really work that much.
But I would be interesting to see if there may be some extension headers which is not dropped, like routing headers.
I still need to measure routing headers. I would say that I would expect them to be dropped probably more than any of the other extension headers that we measure here. Just to give you another example that is not in the internet draft, is not in the slides, but I also measured the extent to which IPsec packets are dropped. IPsec in V6 are extension headers too, and they get dropped too. So even before we're not talking about, of course, probably the final destination or the destination system would drop them because there's no security association, but they are dropped before they get to the, to the intended destination. So I expect them to be dropped too. So what does all this mean? First of all, if you want to use extension headers, you would have to be very lucky. Last year, when I published like an earlier version of a document that I'm going to describe now, my recommendation was that any guy, let's say, producing a protocol that relies on extension headers should at least, well, ideally not really rely on extension headers, but if for some reason they wanted to, they should provide some sort of backup mechanism, okay? Because why? Well, because in many cases extension headers don't work. That generated a lot of discussion, or like a flame war, if you want, at the IETF. So we essentially had to remove all of that from the document. I still think in exactly the same way, but that's not mentioned in the document. But another thing that is nice to consider is that quite a few times people consider that extension headers are awesome for attack purposes. And if they are dropped, I mean, they are not just dropped for legitimate purposes, but also when you're trying to use them to performing attacks. This means that in many cases, if you try to use extension headers to, let's say, do some evil task or some evil, something evil with a remote system, in many cases, the use of extension headers by itself will mean that your packets are dropped before they get, to the target destination. So if you are an attacker, well, extension headers can be awesome if they are not dropped. But in many cases, they are dropped, okay? So rather than, helping you in, let's say, evading a network intrusion detection system or so on, they might also mean that you're actually, helping your target network by, flagging your packets and dropping them. So if you are, again, up to doing something evil, you should probably, first of all, figure out whether your packets are actually getting to the network that you want to attack or penetration test or whatever. Ongoing work in this area. First of all, this is the document that I was mentioning that has results from all these measurements. So if you Google for this document, I think the latest revision was number 02. You will get like a summary of the results that we got when measuring, mail servers, web servers, and name servers. And that document also contains like step-by-step instructions on how to use the IPv6 toolkit to reproduce exactly the same results that we got that we published in the document. The second document here is a document that I think, if my assessment is correct, that has been already adopted by the OPSEC working group. It's a document that essentially provides advice on the filtering of IPv6 extension headers. Unfortunately, I would say that the document, even when I'm a co-author, it doesn't necessarily reflect exactly what I think. So what I would probably do is drop most of them. And in this case, based on feedback that we received from the working group, we are trying to be like, let's say, nicer and trying to allow as many extension headers as possible. So that's something that at times happens, when you work on documents for the IETF. The initial version of your documents reflect 100% or close to what you think. And then as they become adopted and they progress in the process of being published as RFCs, you have to address the comments from many other people, and at times you don't even agree with the document that you author yourself. But there's this other document, RFC 7045, which was published last year, if I recall correctly, which essentially provides advice or clarification to IPv6 implementations regarding what they should be doing with extension headers. This is not operational advice, but rather advice to V6 implementations, okay? And finally, there's this document that we publish that is essentially complementary to this other one. So this one just focuses on the extension headers, without talking about IPv6 options, whereas our document, this one, focuses on IPv6 options. Some comments about the fragment header itself. So this is the syntax of the fragment header. We're not going to, describe each of the fields in here, but when it comes to the discussion that we are going to have right now, what we are interested in is the identification field. This is the same thing that you had in before. An identification number is used to identify fragments that belong to or that identify the same packets. From the IPv4 world, already we know that if you use predictable fragment identification values, that leads to different security implications, the possibility of denial of service attacks and so on. Simplest example would be that if I'm sending him like IPv6 fragments and the fragment ID values that I'm using are predictable, for example, he could send spoof fragments that collide with mine. So now he gets like lots of fragments with the same fragment ID and he doesn't know which of the fragments are legitimate and which of the fragments are not. When I looked at this for the first time, I said, well, all of these implications were known from the v4 world, so probably they are not implemented in v6. So these are some of the results that I got at the time. I recently measured Cisco iOS because there were arguments on the mailing list like, well, yeah, it's true that some implementations were vulnerable to this stuff, but that was only like old implementations. And then I said, okay, let's take a look at some other implementations like Cisco iOS. And Cisco iOS, as far as I have checked, they use predictable fragment IDs. They use a global counter initialized to 0 and incremented by 1 for each outgoing fragment, which is another way of saying the worst possible scheme. Okay. On the other side, some nice things, if you want. At least Solaris and Linux, they patch their fragment ID generation in response to the internet draft that we published. This was back in 2011, if I recall correctly. That's something that is nice. I'm of the idea that publishing documents at times can be nice if you have some sort of idea that deserves it, but things don't really work on paper. So what I personally enjoy is when something that that you publish in a document eventually gets into an implementation. So for me, that of publishing a document, if anything, is, let's say, 50% of the work that needs to be done. The other 50% is getting that implemented. So usually when I publish documents, I try to socialize them with developers from open source operating systems, and that let's say the benefits from that is twofold. On one hand, you get feedback, and maybe they might catch errors or flaws in the scheme that you are proposing, or even if they are not like 100% flaws, they might help you improve the stuff that you did. And the other thing is that if they really like the stuff that you propose, then they might implement that. And for example, I use Linux, so I only get to know the stuff that I design, so to speak, if these guys from Linux get to implement it. So that's something that is nice. Linux and Solaris at least patched this. I had no luck at all with Windows. At the time I was working on this stuff, I was working for a defense organization in the UK, or was doing work for them. And so they kind of like require me to, do the, let's say, responsible disclosure process and blah, blah, blah. At least my experience at the time was that, talking with some of these companies was like a total waste of time. You would end up exchanging like 10, 15 emails, and you wouldn't see any changes at all. Whereas on the other hand, I would say that talking with with developers from open source operating systems, gets you a completely different experience. So typically you get more, first of all, they understand what they are talking about, which is already like a good thing. You usually get like good feedback, and not just that. I mean, usually you finally get the stuff implemented. I think that it took the Linux folks like no more than 2 weeks to get this implemented. Same thing for Open Solaris, okay? There's a tool in the V6 toolkit that allows you to assess the fragment identification policy at the node. So if you run frag6 in this way, so the option is frag ID policy, and then you use the, some sort of destination system. The tool will inform you, what's the, let's say, the algorithm that some implementation is employing. I'm not going to run the tool right now because I'm not sure how good we are in, with the time. But if we, get to the questions section and, we still have enough time, I can run these tools. But it's, extremely easy. Just if you have like, a terminal open, just replace this address with whatever address you want to test. And what the tool will do is it will try to infer whether, for example, the fragment ID generation algorithm produces like random IDs or produces some sort of predictable seconds. When you set the -b option, you also get like a dump of the fragment ID samples that the tool takes. Okay, so even if the tool cannot really figure out whether there is some sort of pattern for the fragment ID values, you could be able to, to infer that yourself. I'm going to skip this, but one of the implications of predictable fragment IDs is the implementation of idle scan. Matthias, he implemented the idle scan. Is it committed to Nmap? So he essentially implemented for Nmap exactly this stuff that I am describing here, which is essentially, you might recall from the IPv4 wall, I don't recall what it was, idle scan call, which essentially means that you can port scan a system without actually sending any packets to that system itself. Just going extremely quickly, so we could very quickly describe how the idle scan works. So let's say that if you are an archer and you wanted to do an idle scan, let's say that this is the zombie system and this is the victim, the one that you want to, to scan. What you do is, first of all, you sample the current, of course, all of this is assuming that the zombie is implementing predictable fragment IDs. So what you do is you would sample the current fragment ID value. So in this case, it's 45,000. Then you send a sync packet to the victim. And if the corresponding port is open, then you get, as a response, the SYNAC and a reset packet from the zombie. Then when you sample the fragment ID again, since the zombie sent a packet here, the fragment ID will be 45,002, okay? Because a different fragment ID is used for each outgoing packet. On the other hand, if you have this scenario in which you have a closed port, you first of all sample the current fragment ID, it is 45,000, then you send the sync packet in here, and since the port is closed, the victim responds with a reset. Now, since you don't need to respond to resets, the zombie here is not going to send any packet, okay? So now when you sample the fragment ID again, the current fragment ID is going to be 45,001, okay? So essentially, if an implementation uses predictable fragment IDs, you are able to tell whether that implementation sent any packets, any fragmented packets between any of your proofs, okay? So we send a proof here, then we can see that this zombie is sending a packet, and then we sample again the fragment ID, and we can tell by the fragment ID values that the zombie sent a packet in between. In this other case, we do the same thing. We sample the fragment ID, then we send our proof packet, and when we sample the fragment ID again, we can tell that there were no packets sent in between because the two fragment IDs are consecutive. So of course, one of the ways to mitigate this attack is essentially not to employ predictable fragment IDs, okay? So we published this document like a while ago, easily 3 years, I guess, 3 years ago. At the time, this document was standard track, So essentially, among other things, well, it described the problem, described the security implications, and also required all V6 implementations to, employ non-predictable fragment ID values. Then there were complaints in the working group, so we changed the track of this document to informational, okay? And I thought, well, that's not what we should have done, but if that will allow us to publish the document, so be it. But this document was recently reviewed by the working group chairs, and they are arguing that this document shouldn't be published at all. For me, that's an extremely bad idea, but it is what it is, okay? At times, when the document was a standards track, the concern from many people is that when we publish standards track documents, those documents give the audience, the public, the idea that IPv6 is still in the works, which is true to some extent. But let's say they just don't want people to realize of that. But it's quite unfortunate. I mean, what's unfortunate is that you are supposed to be doing engineering and you end up doing some sort of marketing. Because if you are publishing or not publishing documents, depending on what people is going to think about those documents or what they are going to infer, that's, from my perspective, not the way to go, but it's something that happens. Some comments on attacks that employ IPv6 extension headers. I'm not going to talk about router advertisement guard evasion or blah, blah, blah. I mean, we have talked so much about this stuff that, I hate to even have to mention this. But there is another attack vector that I ended up coming up like by chance. So this is my reasoning at the time. So we were saying before, before getting into the details, we were saying before that packets that employ IPv6 extension headers are filtered to a large extent on the public IPv6 internet, okay? So again, that means that if a packet employs extension headers, chances are that those packets are going to be dropped, okay? So my reasoning at the time was, what if an attacker could cause a packet to employ extension headers? Okay? So rather than the attacker being the source of those packets, what I'm saying is, let's say that I have a node here communicating with this other node, and somehow I can cause the packets that this node is sending to employ extension headers. If the network itself filters packets with extension headers, then by triggering the use of extension headers, I'm essentially causing a denial of service, okay? So, first of all, you might wonder, well, how can you possibly cause a system to employ IPv6 extension headers? Well, because at least the current specifications state that if you receive an ICMP packet to big message claiming an MTU smaller than 1280, you have to produce what we call IPv6 atomic fragments, which means that you put a fragmentation header in each of the packets that you send. So that's a very clear and easy way to actually trigger the use of extension headers. So now let's consider this scenario. So let's just say that we have this host here, for example, downloading something from this server. And let's just assume that we know that the internet somehow in here is filtering out every packet that employs some sort of extension header. So what could happen is that an attacker here in some part of the network, he sends an ICMP packet to be claiming an MTU smaller than 1280 to the server, and right after that, the server will start sending atomic fragments to the client. Now, if the network didn't filter those packets, to some extent, that's fine. But if the network does filter packets with extension headers, then all of these packets will be dropped, okay? I had this, sample test case, which I guess it's a good thing. It doesn't work anymore. So this means that these guys have, I guess, improved their network to some extent. And the idea was simple. What I was doing, as a sample scenario for you to, to test, I had found out that if you connected to www.kernel.org, on the way, on any way, any path towards www.kernel.org, packets with extension headers were dropped. So the sample scenario that I would make the audience test by themselves was this. First of all, telnet to the IPv6 address of kernel.org, of course, without extension headers at all. So as a result of this, you'd be able to establish a connection, okay? So the goal of this first step was to just double check that communication with that site was working properly. Then the second step was to spoof an ICMP packet to big message claiming an MTU smaller than 1280. This is the IPv6 address of www.kernel.org, and this should be your own IPv6 address. Okay, so if you want to try this on your own system, you should do ifconfig or whatever to learn your own IPv6 address, and you should replace the one in blue with your own IPv6 address. Why? Because the idea is that you are going to attack, to some extent, your connection with www.kernel.org. I mean, you could attack any connection, but since the goal here was for you to easily measure that this attack works, we just wanted to attack your own connection as opposed to someone else's connection. And then, after sending this packet, you try the same thing again. I mean, this is the same command that you had executed here. Now, the thing is that if this worked as expected, in response to this packet that you just sent, then after that, kernel.org would send you every single packet with a fragment header, okay? And since the network was filtering fragmented traffic, you'll never be able to connect to kernel.org again. Or not never, only after, let's say, about 10 minutes. Because for 10 minutes, the information that fragmentation needs to be used for that communication instance is like cached. I tested this yesterday, and this ADAC wouldn't work anymore. I would assume there are two possibilities. I guess that one of them is that there is some sort of filtering device that filters the ICMP packet to big messages that claim an MTU smaller than 1280. In this case, we were claiming an MTU of 1000, right? So these are the ICMP packets that trigger the use of fragmentation. So I guess that in response to these tests that we did, someone set up some sort of filter in there. But you could possibly, I mean, this is just one example. You could possibly find, other, let's say, public web servers, whereas on the way to the web server, the network filters packets with, a fragment header. So the same attack would work. Yes?
At this point of time, a Linux node doesn't, the kernel itself isn't protected anymore currently.
Yes, they committed the change less than a month ago. Yes.
So if they're running the latest kernel, which I would assume on kernel.org,
Yes, that could be the reason. Yes. So I don't know if it's mentioned later, but I author an internet draft on this topic, and essentially what the draft says is that you should never generate atomic fragments. So if you get an ICMP packet claiming an MTU smaller than 1280, just drop it. Linux, they implemented and committed, this change like I think a month ago or so. So if you are running a current kernel, it wouldn't be vulnerable to this stuff anymore. But you're right what you're saying. I mean, you would expect kernel.org to run the latest kernel. But at the same time, sometimes you have those servers being operated by people that are not necessarily closely related with the developers. So yes, that could be one of the explanations for that. Yes.
another question out of interest. So if I send this ICMP6 message, usually isn't the server sending atomic fragments to all nodes on the path? So if I sit here and do this, shouldn't it then send atomic fragments to every host within this network?
No. At least as far as the specification goes, when you receive a packet-to-bit message, you send atomic fragment, but just for communications that involve the two IPv6 addresses reported in the error message. No. I mean, that could be, I mean, if you ask me, I mean, I'm just thinking out loud, you could think of that as an optimization. Because if I had two nodes on the same network, chances are that the path is going to be the same. But at least as far as the specifications go, the error message just affects the communication between two specific IPv6 addresses. One thing that is interesting here is that in order to perform this attack, you only need to know the two IPv6 addresses involved, nothing more than that. You don't need sequence numbers, you don't need port numbers, you don't need any other thing like that. The reason being that many implementations, they don't do any kind of validation check at all on the ICMP error messages. So for example, in the IPv4 case, they used to check, for example, the TCP sequence number and so on. But in the IPv6 case, most of them, they don't check anything in the error message. Now there's another scenario which I honestly didn't check in practice, but for many, well, if I had tested this in practice, I wouldn't say it anyway, to be honest. But let's just consider this scenario. Let's just say that you have two BGP peers, okay? And let's say that for security reasons, these two BGP routers are dropping IPv6 fragments. That's not an uncommon policy. I mean, usually fragmentation is seen as, evil. So it's not unusual for BGP routers to drop IPv6 fragments. So let's just assume that, again, the routers filter out IPv6 fragments, but they still allow ICMP error messages. So you have the two BGP peers here. You spoof ICMP packets to both of them or one of them. Now they start employing IPv6 atomic fragments, but since they drop packets that employ fragmentation, now they are performing a denial of service. They are DOSing themselves, okay? Now you might wonder, well, but this shouldn't work because they might be employing TCP MD5 option or they might be employing IPsec. Not really, because IPsec, TCP, MD5 and everything, all of that works above the fragmentation layer, okay? So this would cause packets to be discarded even, IPsec or TCP MD5 get into the game. Of course, the implications of that should be straightforward. If you were able to essentially, cause the connection between two BGP peers to fail, essentially you could cause a denial of service to the whole network. I didn't test this myself. If you are an operator and are running a BGP router, you should probably try this. I didn't, okay? So how could you possibly mitigate these issues? Well, this document essentially mitigates these issues by updating the corresponding specifications by saying you should never generate IPv6 atomic fragments. They are a bad idea. That's all that you can say about that. So this document forbids the generation of atomic fragments, and it also updates SID. SID is like B6 before translation, so that SID doesn't rely on these atomic fragments anymore. As we were mentioning already, this has already been adopted by the Linux kernel. It's interesting because at the time there was some resistance in the IETF, to, let's say, adopt this document. And for me, it was like, whatever, I mean, it's in Linux already. So that's, another benefit of socializing stuff with, developers. I mean, no matter what, for example, the IETF ends up doing, I mean, Linux nowadays has like a large market share, if you want. So if there's something that, doesn't work for Linux, that being Android and every, Linux variant, opposing to that is like being clueless. So you could argue that this is a battle that was won already. I mean, there was some sort of strong opposition at the time against this document, but Linux implemented this. It's already in the kernel, and the document was adopted. This one in last November too. Yes.
A small comment, so if you implement this and you duplicate the atomic fragments, then the idle scan also doesn't work.
Exactly, yes. So yeah, the idea essentially is that atomic fragments are a bad idea. So, a few years ago when I wrote an RFC on atomic fragments, on how you should process the atomic fragments, I said, okay, well, if you are careful enough when you process them, it's okay. But then, the more you look at atomic fragments, the less they make sense. So the idea is that, atomic fragments are a bad idea. Stop using them. A couple of comments on some ongoing work on neighbor discovery. If you look at neighbor discovery implementations, they are extremely bad at validating neighbor discovery options. A simple example is the use of source link layer addresses and target link layer addresses options. These are the options that embed the MAC address corresponding to some IPv6 address. And one thing that you can do, and with many implementations, with most, the ones that I have tested, it works. You can make a unicast IPv6 address map into a broadcast or multicast link layer address. So what are the things that you can possibly do with that? So one simple case would be this one. So let's just say that you are on a switched network and you want to sniff traffic, the packets that are being sent between two different systems. One of the possible ways, or the way you do it in the IPv4 world, would be to spoof a lot of R packets so that you confuse the switch, and then the switch ends up broadcasting the packets to all of the nodes. But let's say like a more interesting way of doing that is you play with neighbor discovery, and you perform like a neighbor discovery cache poisoning attack, and you make each of the two involved IPv6 addresses map to a multicast address, for example, or even a broadcast address. That means that when this system wants to send packets to this other system, at the link layer, it will use broadcast addresses. So it means that the packets are going to be sent to all of the nodes on the local network, okay? When I came up with this idea, I said, well, this can possibly work, right? That would be completely stupid. Well, it is completely stupid, but it does work, okay? So if you perform like a neighbor cache attack, like same attacks that are well known for years, and you rather than using your MAC address, you employ like the broadcast address, like all Fs, or you use the all nodes address, like 33.33.00.001. You will see that it works as charm. And if you try that with a switch, for example, you will be able to sniff the traffic without having to send like lots of packets to confuse the switch. This is like a very, let's say, academic or clean way of sniffing traffic in a switched network in V6. To be honest, then I wonder, I never tried whether this works in the IPv4 world. Because sometimes it's interesting, when you have a V4 attack, to try to port it to V6, and when you have something in V6, try to port it to V4. I haven't checked whether the ARP implementations, they perform validation checks, but this is stuff that does work in V6. At least it works for Linux, and at least it works for BSDs. I haven't, tested this in that many other operating systems. So we authored this document. I don't recall if the name was exactly this, or it's draft ATF 6-month IPv6 ND op validation, but the file name is something like that. And the document is extremely simple. It's a standard struct document that updates RFC 4861, the RFC on neighbor discovery, and it requires validation checks to be performed on neighbor discovery options, okay? So the idea is that we try to formally enforce requirements so that neighbor discovery implementations, they are not vulnerable to these sort of attacks. Some comments about operational issues. Comments on first hop security. I'm not going to talk about router advertisement guard. I talked about that already last year. We published an RFC describing how to evade router advertisement guard and with implementation guidance on how to prevent those evasion attacks. But the document that I'm going to talk about a little bit is the DHCP version 6 shield. This is like IPv6 version of DHCP snooping, or if you want to see it in a different way, it's like router advertisement guard, but for DHCP version 6. The idea is very simple. If you have a switch in here, you can tell the switch, you should only allow DHCP server packets on this specific port. Now, if you get DHCP server packets on any of the other ports, you should drop them. And in that way, you can prevent, DHCP-based attacks from happening. The tricky part, of course, is, how to prevent the use of extension headers from evading this mechanism. So one of the things that this document does is, provide like clear rules on how you should process packets so that even if the attacker employs extension headers, he cannot, evade your device. For me, this document is like extremely obvious, particularly when it's heavily based on router advertisement guard. It was sent to the ISG for publication, and there is an area director that is still saying that if a packet contains an unknown extension header, you should let the packet pass the device. No way, right? But that's where the document is stuck. I mean, you should be paranoid by default. If you don't understand the packet, you drop it. But this area director is arguing the other way. So this document has been like stuck in that place for easily 2 months now. That's what I can say. And I was talking with my area director, the area director from the operations area, like saying, we are stuck in there. I mean, it would be extremely nonsensical to apply the change that I'm being suggested. So I had two options, like fighting, this battle, or essentially screwing up the document altogether, like producing a specification that by design is broken. So that's where we are at. Hopefully next week at the IETF meeting we will be able to make progress on this. There's a document that we publish on V6 firewalls. V6 firewalls is a topic on which I personally think that there's lots of work to be done. For many reasons, nobody really knows what the V6 firewall should do from many different aspects. So if you try to, let's say, buy a V6 firewall, you don't really know what you should be requiring on that box. So we published this internet draft that tries to, list a number of requirements that every single firewall should implement. As you would expect, vendors argued against this document because, well, if you have a set of requirements, they should comply with those requirements. And that would prevent them from, shipping crappy V6 firewalls. So they probably want to keep doing money with that. And I guess that this document is going to have a hard time moving forward. Another document that made progress, this is a document that I presented last year, a document on VPN leakages. The idea is extremely simple. Let's just assume that you have an OpenVPN server at home, and when you travel around, let's say when you attend a security conference, you run OpenVPN so that you tunnel all your traffic to that box that you have at home. Okay? This could be, and you have like a very nice case here at this conference. So what's the problem? If you look at many VPN implementations, they only support IPv4. Now what happens? You are running, for example, OpenVPN, and you assume that all your traffic is being tunneled in a secure way to that box that you have at home. In that way, you can prevent, let's say, people from sniffing your traffic on the local network. But what happens, for example, if the network, like this one, supports IPv6? Well, whenever you are communicating with a site that is dual stack, that is, supports V4 and V6, if you end up employing V6, then all of that traffic goes in the clear. Why? Because your VPN implementation knows nothing about IPv6. So it's only able to tunnel V4 packets, but when you send IPv6 traffic, the VPN implementation doesn't understand anything about V6, so it sends the traffic in the clear. So there's a perfect example in this network. This network is dual stack, so if you are employing, for example, OpenVPN, at least some version that I was employing didn't have any V6 support at all. But even if the VPN implementation has v6 support, there's lots of tricks that you could play to actually confuse the VPN implementation and still have the VPN implementation send the v6 traffic in the clear. For example, you could send routed advertisement messages advertising more specific routes. So rather than your packets, rather than the packets being tunneled on top of the VPN, they are again sent out in the clear. Conclusions, these are the same from last year. If you look at v4 and v6, you essentially find the same issues. You never know whether if it's just that we didn't learn the lessons from before, whether there was different people working on v6 than before. So the people hitting these problems in v6 is because they never actually experienced the same problems in before. Or another option is that the v6 specifications could have been way better, and in that way we could have avoided many of the problems that we are discussing. My take is that probably it's a combination of all of these items. We didn't learn the lessons from before. There's also different people working on v6 than they were working on before. If you look, for example, at the commits on the v6 code, for example, when it comes to the BSD stack, it was implemented by people from Japan, whereas the IPv4 stack in BSD, it was implemented by people in the University of California. So that's a clear example that different people produce both stacks. And from my perspective, it's also true that the specifications could be made much better, and that could have helped us avoid many of the problems that we have faced. Questions? Yes.
One remark, considering the development of IPv6, I think many of the security vulnerabilities in IPv4 were detected after IPv6 was designed. After 2460, VRC. And so this was one backpoint for IPv6.
Yeah, that's true. What I personally think is, what you're saying is true. Probably, yeah, I mean, I think 2460 probably is dated like 1998. Well, there's a previous version of it, because that's not and the previous version probably is a couple of years, dates from a few years before. But I mean, even then, I would say that, for example, even when you think about, let's say, the year 2000, there was virtually no v6 deployment at all. So what I'm saying is that even if those problems were found before, once the v6 core specification had been published, there was still time to patch the specifications before we got to this point where we need to deploy v6, and we find that the specs still need to be patched, implementations still need to be patched, and so on. From my point of view, when I approached v6, I was kind of like curious in the sense that, when it comes to, let's say, IPv4 or protocols such as TCP, they are protocols that, even if you like them or not, they have been successful in the sense that everyone uses them. And nobody can, say that they have not had an impact on society or whatever. So you could expect people like, the guys that wrote the v4 or the TCP specifications to be jealous about their little successful baby, right? But then you have v6, which is a protocol that, I mean, has not been that much used. And you still find these people that are jealous about their unsuccessful little baby. You know what I mean? So that's something that I was curious about. If I was on the other side, I would have taken like a different attitude. Okay, let's try to improve the protocol as much as possible. So eventually we remove as many problems as possible, and we get like better deployment. But unfortunately, that has not been the case. So, well, if you have any more questions, feel free to drop me an email or just talk to me in the corridors. Again, this is the address of the v6 hacker list. If you are interested, I mean, I never made this comment, but I have the plan to try to do a v6 hackers meeting in July this year, around probably in Prague, where the ITF meeting is going to be held. I'm not sure if it's easy for people from here to fly there. But that's the goal that we have. We had the first IPv6 hackers meeting in Berlin 2 years ago, so this would be the second. Okay, so thank you.